That I'm using this time-memory trade-off instead of space-time trade-off. And I actually wanted to highlight one particular thing here, which is this is a different type of results, and it's a different problem than the ones that we looked at before in this session. So I don't know. I was wondering if the organizers were aware, but that's going to be also the case for Itai's talk after mine. So we are really looking at a different thing where what we are looking at is not the amount of side information, non-auxiliary side information that you're getting from pre-computation, but rather here space is memory. So that's why I call them time-memory trade-offs, because we are looking at the memory the adversary has during its execution, and we just want to find trade-offs, lower bound trade-offs between space and time of the adversary. So in particular, this line of work really fits within the broader picture of understanding the concrete security of arbitrary cryptographic schemes, having things about encryption, authentication, and whatnot. Things that we can analyze quite precisely. So what we would like to understand, given a certain amount of resources that the adversary has, how well can the adversary break the scheme in terms of its advantage. And so we can do this, of course, on both ends, right? So on the one hand, we can have proofs, right? And this is, by the way, another message I want to send you here if you're trying to squeeze your talk into this program, or you still have to come up with a good story, that everything can be a lower bound, right? So either you give a security proof, which is an upper bound on the advantage, or a lower bound on the amount of resources, or you can give an attack, which is a lower bound on the advantage, or an upper bound on the amount of resources. You pick whichever you want, and you can fit all of crypto into a lower bound, right? But you can do both here, right? So you need to do both if you want to understand the exact security of a scheme. But I want to highlight here that, at least in terms of communities, we usually do different things when we think about resources, right? So usually in security proofs, when we think about resources, we think about time complexity or maybe circuit complexity, if you're one of those who like that, or things related to that like query complexity. But if you look at cryptanalysis and attacks, then usually resources are more complex. You really want to understand which attacks are feasible and which ones are not, and then you might look at things like memory or parallelism and so on. Right, and this is important because even given equal time complexity, your attack may require a lot of memory and be completely infeasible. Or you might have an attack which is memoryless, and that's much better. Right? So the goal here of these types of works is to actually introduce memory into the picture of provable security and sort of close this gap. And this can be very important because given a certain fixed time complexity you might be concerned with, depending on how much memory the adversary has, your scheme might end up being much more secure if the memory is bounded than if it's not. And in many cases, it is realistic to assume that you don't have much memory. Or you can have at most a certain number of bits, which is the entire storage that the NSA can have, and still that's a reasonable number. Okay. So, and I want to illustrate now the type of things we look at with a simple example. And in particular, we're going to look at the simplest encryption scheme that you can think of that we build out of a pseudorandom function, which is going to be already quite interesting. So you can ask the same question for any other scheme, but this is going to be simple enough and hopefully enlightening. So, and this is a scheme that just encrypts a message M into a ciphertext which consists of the randomness and then the PRF evaluated on the randomness, and you XOR the output with the message, right? And of course, we know if you want to prove concrete security of this, say in terms of indistinguishability from random ciphertext, so that's a notion I'm going to consider now, and I want to give a concrete theorem. You can, for example, look at the real or random advantage, which is exactly tells us for a certain bound of the running time phi and a certain amount of queries q. So how well can you distinguish q adaptively chosen encryptions from corresponding random ciphertext, right? And we can easily bound this advantage in terms of the PRF advantage for the underlying PRF, plus an additional term q squared over 2 to the n, which is going to tell us that you cannot expect security if you encrypt more than 2 to the n over 2 plain text, okay? So I hope you're fine with this notation. It's actually kind of a bit informal, but if no complaints are there, otherwise ask questions. No, you're not fine. Well, well, first of all, we have to see if it's only your opinion or everyone else's opinion, but I trust your opinion. Okay, live with it. Okay, so, all right. So now this term, right, so is actually tight because it corresponds to a simple attack where you get an adversary. So I'm saying very basic. It's going to be all about basic stuff. So Itai afterward is going to give you the hard talk about problems here. So the adversary, so I said you look at the adversary, they just encrypts, say, gets multiple encryption of 0, say q of them, and then just waits for a collision in the randomness, and then if you have a collision in the randomness, you check if you have a collision in the other part of the ciphertext, and if that's the case, of course, you're more likely to be seeing a real ciphertext than a random ciphertext, and this achieves advantage roughly q squared over 2 to the n, right? But now starting looking at what we care about, one important point here is that for this attacker to work, you need to remember all of the ciphertexts you've seen so far. Right? So the space complexity or the memory complexity is roughly proportional to the number of queries. If now you want to save on that, you can come up with a different adversary that, for example, only store S of the ciphertext is C, so S is a parameter here. And then, well, as you see in your ciphertext, you're going to only check equality of the randomness with one of the ciphertexts you're storing. And otherwise the other ones you forget, and then do the same decision as before, right? And now you're saving space, but you're also losing advantage. So now your advantage is going to be roughly S times Q over 2 to the N. So if these attacks were optimal, then this will suggest that there's a trade-off between the query complexity and the space complexity, right? So if you want to break the scheme with good probability, then you roughly have to have Q times S equal to the N. Okay, so we would like to prove that this is optimal, right? So that means kind of changing our initial theorem, which is the style of theorem you will have in a textbook, right, to something that takes into account also the memory complexity of the adversary. And hopefully this q squared over 2 to the n term is going to become some s times q over 2 to the n term. Okay. And of course, that's something we're not used to do. So if you want to use standard tools here, you know that you don't know how to do it. Okay. So that's the thing. So now I want to show you first a very simple proof in retrospect that gives us actually something very close to the optimal expectation that we have here. Namely, it's going to give us a bound, which is essentially what I just claimed, except that the s times q over 2 to the n term has a square root on it. So if you're one of those people who's only concerned in knowing, when do I get good probability for which s and q, then it doesn't matter because square root of 1 is still 1. If you're really concerned about the square root instead, then actually something can be done to get rid of it, which is non-trivial, but I'm not sure yet what's the final theorem there, so I don't want to state a false theorem. And so this is going to be pedagogical enough to look at it. Okay, so we want to prove this. And we're going to do this by using basic information theoretic tools, and it's going to be quite different from the way you will normally prove security, say, in your Crypto 101 class of such a scheme. Okay? So the starting point, however, is the same, right? So you do some basic trivial stuff that you will always do. You first replace in the real ciphertext your PRF with a true random function, right? You pay a term here, which is the PRF advantage. And then the real problem is to now distinguish this ciphertext generated with the actual scheme, but with a random function from truly random ciphertext, but given now a bound on the memory of the adversary, right? And in fact, the message here is kind of just a syntactic distraction. So the basic problem is, doesn't even have a message, right? So you can reduce it easily to just this setting where you're given either some sample which looks at the random Ri, and then the random function, the same random function across all samples applied to Ri, versus some truly random samples, right? And note that they're not the same, because on the left-hand side, if you get the same Ri twice, then the second part of the pair is going to be the same, right? Which is not the case on the right-hand side. And now you would like to prove some indistinguishability statement about these two worlds. And actually, this is a special case for something more general, which you think is a very natural setting that, however, I don't think, and someone feel free to correct me, was explicitly considered in the literature before, in the streaming literature. And what I refer here to streaming indistinguishability, so this is a setting where we are looking at two different streams that are, say, q random variable each. They could be correlated, they could be any distributions. And now you compare to settings where a memory-bounded adversary gets one variable at a time, but between each step can only store s bits of information, and then can output a decision bit, and you want to say how well this adversary can tell the two streams apart, right? So contrary to the usual setting of streaming algorithm, this is like average case, it's not worst case, it's a distributional statement, and also you're not computing any specific property of a stream, you really want to distinguish two distributions. Okay?
I think Yao used exactly the same slides in one of his talks. It was like 1989.
Were you there? Yeah, so that's exactly what I was looking for, right? Yeah, good. So, right, but I mean, I'm not claiming it, so, but I think the setting hasn't been studied as much as it should be. I mean, someone might have thought of it, okay? So in any case, that's a special case of that. And so one thing we're going to do here is, we want to apply this to the simple encryption scheme I just gave you. And now, so in this particular case, what is going to be convenient, and hopefully maybe you'll see why in 2 slides, is to kind of take a slight detour in terms of techniques into information theory. And even though we are bounding kind of a statistical type distance or advantage there, so what we're going to do, we're going to take kind of a Shannon-like approach to this. And essentially, this is essentially Pinsker's inequality and some, I'm not going to prove this, and some hybrid argument using KL divergence. But essentially, what it boils down to is that to a statement that says that the advantage is upper bounded by the square root of the overall. So if one of the two streams is random, say the first one, and every random variable is independent from a universe of size m, then what we look under the square root is the difference between the overall entropy of the upper stream minus the sum of the conditional entropies of each variable yi in the second stream conditioned on the state just prior to learning that variable. Right? And this here, entropy is really Shannon entropy and the corresponding notion of conditional Shannon entropy. Okay? Or you can prove this as a little exercise. Okay? Yeah, M is the size of the set. So it's a universe where you pick the xi. So, and you can think that the yi are also from the same set. There might be a subset, but yeah. Yeah, Benny?
Is it in some sense generalization of what we all know, like the next big unpredictability is that when you look at the PLGs? Like,
yeah, so it's
in these terms?
yeah, so you can think about it in, I mean, it's essentially just a hybrid argument. But I'm taking into account the memory, right, for the conditioning, and I'm taking it to the KL divergence regime. So yeah, it's morally is the same, yeah. But it's going to be important for at least this type of proof I'm going to give that we are looking at Shannon-like, and you'll see why in a second. Is there another question? Okay, no. All right. So now the nice thing is that, so for our particular setting, so this is going to give us a super easy proof, which is going to give us exactly the right thing. Namely, so now again, our stream, now the xi are going to be the random things. So now I kind of switch them, so 2n bits. And the other ones are the actual thing. We're looking at the real samples. And now we want to compute the entropy of the yi given the state prior to learning yi. And now we can just use, and if you're not familiar with Shannon entropy, you forgot everything, just remember that Shannon entropy has all of the properties you wish to have from an entropy measure. Okay? So, and that's nice here because that's all you need to know. Okay? So you can use first the chain rule, right? To say that the entropy of yi, so it's made of Ri and Rf of Ri. So you first compute the entropy of Ri given the state plus the entropy of Rf of Ri given the state and Ri, right? Now the first entropy is clearly n because Ri is independent from the state. The second entropy, it's actually the interesting part. You can first use the definition of conditional entropy. And so you're going to get here, so you take the sum over the random function output on each x, condition on the state, and then take the average. And now the nice thing is that, again, you're looking, we actually need to compute a lower bound because there was this minus sign there to get an upper bound of the advantage. And so now here, so the sum of the entropy of the random function output of each x is actually the entropy, is lower bounded by the entropy of the entire function table condition on the state. Okay, it's not equal because there is this conditioning. Okay, otherwise it will be equal. Okay, but now the other interesting fact, right, that's what you will expect. If I actually have a state which is s bit of information about the past, right, this can reduce the entropy of the entire function table by at most s bits. And now I know what the entropy of the function table of a random function is just 2 to the n times n, right? And if I plug in the number, I'm going to get this is exactly 2n minus s over 2 to the n. The xi comes from a set of 2n bits. So if I plug in everything, I'm going to get exactly a square root of q times s over 2 to the n. Now the question is why am I doing this detour to Shannon entropy? I don't have really a slide. You could have done, well, why don't I just compute the statistical distance and then take just a regular hybrid argument? Actually, that goes back to Xiao's talk in the prior session. If I actually did that, I just look at the statistical distance condition on my s-bit state. Actually, the best I can expect is square root of s over n. And then if I take a hybrid argument with q hybrids, I get q times square root of s over n, which is nothing interesting, right? So that's why we're doing this in the Shannon regime. Okay. So another interesting fact, which is really, again, motivated already by this basic question here, but it kind of came up if you want to explain this to practitioners and analyze real encryption schemes, is that in practice, your PRF-E will actually be implemented by something like AES, right, by a block cipher. And the catch with that is that a block cipher implements a permutation for every value of the key. And so the best PRF security that you can expect here is only up to the birthday bound. So that's say q squared over 2 to the n is a lower bound on the advantage because after that you start, so after 2 to the n over 2 queries, you start seeing collision in a random function and you know you're not interacting with the block cipher. And so, of course, normally what we teach our students to do is that you can apply the switching lemma. So normally you should measure security of a block cipher in terms of the PRP security, which measure indistinguishability from a random permutation, and they're closed and they're related by a term of q squared over 2 to the n. Right? And this could be much better, the PRP security for a block cipher. But when you now plug it in our thing, right, it kind of doesn't make sense, right? Because you were actually proving this trade-off to say things like the following. If your memory is small, then you can encrypt way more than 2 to the n over 2 messages and still get security. But now this q squared over 2 to the n term just spoils everything because it still bounds the number of encryptions to 2 to the n over 2. So maybe you could hope to do something better if you take memory restriction into account and you say, well, maybe the switching lemma is better. It gives me this difference of something like square root of s times q over 2 to the n between the PRF and the PRP advantage if I bound the memory to S. Is that true? Just, okay, Itai knows the answer, but. Okay, so actually no. So, and the point is that, so if I'm given access to Oracle access to either a random function or a random permutation, so the random function will have collisions with extremely high probability. The random permutation never has them. And we have memory-less algorithms that with around the same complexity, 2 to the n over 2, given Oracle access to a function with collision, a random function will find collisions for it, right? So they're based on Floyd cycle finding type of algorithms. So which means that you can really distinguish between a random function and a random permutation with 2 to the n over 2 queries, even if you have little memory. So you cannot hope for any improvement. So you cannot really hope to do this better. But actually what turns out to be the case is that if you want to apply the switching lemma to something like such a simple encryption scheme, in fact, in most cases, the type of inputs you give to your random function or permutation are restricted. And so they are restricted to either being random or to being distinct. Random doesn't imply distinct because we are looking at regimes where you might have collision. And it turned out that there actually we can prove a version of the switching lemma for such restricted types of queries. And here, so I'm not going to say more. So Itai's talk is going to be all about it. But the historical context here is that we did have a proof of this, and it's absolutely non-trivial. And it was actually it was a conditional result based on a combinatorial conjecture on hypergraphs, which I still think is very plausible, but it's very hard to prove beyond what we can prove now. So Itai has a proof that actually reduced to something where we can prove an unconditional lower bound, namely to lower communication complexity, lower bounds of disjointness, and actually prove something better without a square root, which is, you will see that in the next talk. But just you see, so such basic results, right? So in the memory boundary regime becomes a very interesting theoretical problems, right? And that's not the kind of things we were asking ourselves before.
But for distinct, isn't permutation and function exactly the same?
No, because after, if you query it on even if I just get, so essentially what you're seeing, right? If you query a random function, you're seeing a bunch of independent outputs. If you're querying a random permutation, you're seeing outputs that are, individually uniform but distinct overall, right? So after 2 to the n over 2, you're going to be able to tell the difference. Right? So in fact, the underlying question is just that. We'll give you two streams. One is independent random values. The other one is random but distinct. Can you tell them apart if your memory bounded and how well? So which is a very neat question, which is interesting beyond this. And that's what Itai is going to talk about. OK. So I want to mention some other things. Where's the chair? How am I doing on time, Iftach? 10 minutes, perfect. OK. So another thing I wanted to mention, so there's many more things I want to talk about, but I'll stick with encryption-related things because we are already in that mindset. Symmetric encryption-related things is that you might also want to you might not be happy with these trade-offs of like s times q over 2 to the n. So in subsetting, you might hope for more extreme trade-offs that are not these linear trade-offs. And so you can look at different types of schemes and wonder whether they are better or not. And something we looked actually in a paper, so with Aishwarya before, the ones I was talking about before, was actually a generic type of schemes, which is kind of very natural, generalizes counter mode in a way, so or like the simple scheme I gave you before, where you're essentially not picking a random R as a randomness, but say k random values, and then a seed for an extractor each time you encrypt. And then you're going to evaluate your PRF at these k random points, and then apply an extractor to this to get something which you're going to use as a mask for the plaintext. And this is very reminiscent of design of pseudo-random generator against space-bounded computations that have been looked at in the 90s. Okay? And so the basic problem, again, is the streaming indistinguishability problem. So where I'm given either this random version of the ciphertext, where the extractor output mask is random, or the actual output, but where I use a random function instead of a PRF. Right, then just a brief intuition why this gives you some security. I'm not saying this is a tight bound, but just as a starting point, is the fact that when you now analyze the real stream here, then when you just stop, say, imagine you freeze the execution at some point and you have S bit of information that you got there at some point in the execution, and now you get the next sample, then somehow, because you only keep S bit of information, you can expect that if you now sample some random R1 to Rk, and then you evaluate the random, you look at the concatenation of the random function outputs on this R1 to Rk, then it still has some entropy, some mean entropy from which you can extract. And this is just a scaled up version of a problem that comes up every now and then in different forms. I mean, again, starting from Nissen and Zuckerman, and then Salil's work on locally computable extractors for the bounded storage model, and Yevgeny's work on bounded retrieval model, I guess, and then again, recent work on big key crypto. So there's a lot of work on bounds for this. And so you can already instantiate this in different ways, and if you don't care too much about how large K is, say K can be security parameter large, you can get theorems that show you some much better trade-offs. So for example, you can encrypt even beyond 2 to the n messages and still get security, okay? Yeah. The memory?
Yeah, the memory of your
I mean, individual ciphertexts are not going to be, right? So so you can think of your, once you switch away from the PRF, right, to random function, you have this huge random table in the sky, right, which is your random function, and that's larger than the memory of the adversary, right? So it boils down again to, this usual phenomenon that you have in the bounded storage model, and so on. It's just different types of efficiency and games you're looking at. Well, I need H infinity because I need to analyze the extractor. So 2 things, okay, obviously, so smooth mean entropy works, as you pointed out even yesterday. And also the other, you might get better. So one thing is that using the same techniques as I had before, so it's enough to get an extractor, even though we didn't need it there because we were really interested in asymptotic result about K. But if you really want to optimize, that's what we're doing now in follow-up work. So you can actually look at extractors for KL divergence, which gives you better parameters. And then you're going to get over a square root over the things, but it might be better. Okay. And so another point here is that you're looking at the regime of security that are above 2 to the n. So you need to be very careful that if you really care about this, you have to make a very strong assumption on your PRF. Make sure it's still secure. In particular, you have key recovery attacks against a PRF that are memoryless. So this means that at the very least, this PRF needs to have a long key. So it's not, you might be comfortable with this or not as an assumption, depending which area you work on. Okay, so an interesting work here going on right now is that it's interesting to figure out how small can K be, okay, here. Okay, so I wanted to point out that all of these 2 things, so that's the last 5 minutes, we're about this streaming setting, so we're looking at encryption, it's kind of adapting, but it's kind of not in the analysis. So these make doing things much simpler. And I want to show you just one example, again motivated from basic textbook question in symmetric crypto, that shows you how things become much less trivial, okay, if you look at things where there's more adaptivity in the game. And this is about analyzing simple double encryption. So this is just a setting where you have a block cipher, you apply twice with different keys, and you look at the output. And most of you probably teach in class that this doesn't buy you anything in terms of security. But it does a little bit if you're interested about advantage. So there are analyses in the ideal cipher model, so where you choose your block cipher to be a random block cipher. And initial work by Aiello already et al. In the 1990s showed bound that show that if you parameterize this in terms of the oracle query, so to the permutation, or either the random permutation or the construction, and the queries you make to the ideal cipher, you get a bound which is roughly p over 2 to the k length square, okay? Which is consistent with the fact that you can break it with an effort equivalent to key search, right? And the optimal attack here is a meet in the middle attack that essentially what it does, say for the simple case where the key is short enough compared to the input length, it simply just gets 1 point. So evaluate either the construction or the random permutation of 1 point, get the output. And then what you do locally is that you evaluate the block cipher forward on X star for all keys, create a table, evaluate it backwards on Y star for all keys, create a table, and then see if there's a match. If there's a match, you're likely to interact with the real construction, otherwise it's a random permutation. So this works. Now the point is, again, how much memory do you need? Well, the memory is linear in the size of the key space. Okay. And the question is whether this is optimal. right? And initially, you will think this is an innocent-looking question. This is in an ideal model. It's completely information theoretic techniques. You should be able to say something. But it turns out to actually that not be the case. And so in particular, if you look already at this attack, it's related to a generalized version of this, which is a problem that I call it least disjointness. And it's a special case of a problem called element distinctness that has been looked at in the context of space-time trade-offs for branching programs. And the problem I formulated as follows. So you have two lists as an input, which contain k elements from some ground set. Doesn't matter too much what it is. And then you have an algorithm which is bounded in memory. And what it can do, it can ask queries, like either a selector of which one of the lists and an index, so B and I, and then learns the ith element of the list LB. Okay, either L0 or L1 or L2. Right? And that can do this p times, so these queries. And then at the end, just outputs a bit. Okay, and what we would like here is this adversary is sort of to tell apart, to separate the cases where the two lists either intersect at exactly one element, so they contain, so it's not quite intersection, but I think you understand this abuse of notation. So yeah, perfect. So it's either they intersect at one element or they are distinct, so they don't have any common element. So and you would like to be a difference in probability, so the algorithm can be randomized, a difference in epsilon in gap between the probability at which at least you output 1 if the intersection is 1, or at most you output 1 if the intersection is empty. And actually, this problem is really, really hard, so even for the more general element distinctness. So you can give lower bounds or upper bounds on epsilon, depending how you think about it, if you restrict the class of algorithms to say read once or some multi-passes branching programs. But otherwise, we don't have any general insight. And in fact, there are algorithms that look optimal. There's a paper by Beam et al. At Fox in 13, which actually boils back to more heuristic techniques from the 90s in the cryptanalysis community that actually show some non-trivial trade-offs here. Okay? And actually, so you can see directly, this is very close to what we were doing before. We had some lists that came from evaluating the block cipher forward and backwards. You can get points on demand by evaluating the block cipher. And we need to find an element. There's either one element exactly common in both or none. Okay?
The common element would be in different positions.
It would be in different position, yeah. So it's an I and a J, exactly. Yeah, very important, good point. So you have this kind of elementary fact, right, that if you have an algorithm which runs in space S and makes p queries for this problem, for the least disjointness problem of size k, then you immediately get a distinguisher for double encryption. That's the kind of the attack part. But what's interesting, and unfortunately I don't have time to show here, is that actually the connection holds also in the other direction. And that's more surprising at first because the attack, the optimal attack, an attack against the double encryption might not follow this kind of meet in the middle like paradigm, might do any other thing. In fact, even regardless of how many queries you make to the actual permutation, if you have an attacker that succeeds in distinguishing double encryption, then you can build an equivalent space complexity and with a query complexity that corresponds to the ideal cipher query algorithm that solves least distinctness. There's a star here because it's actually kind of in the random oracle model. But I mean the algorithm needs access to some random oracle which is independent of the instance. Doesn't seem to help in any way for the hardness of the problem. And in fact, even the algorithms that I mentioned before from Beam et al. From Fox 13 assume you're given a random oracle to implement some good hashing in the algorithm. So in particular, if you assume that the algorithm is optimal, right? So if you're kind of a positive person, right, you can spin this into getting a lower bound for the complexity of breaking double encryption that actually shows that existing attacks are optimal. Okay? But it's an example where you have some very simple looking problem. It's all information theoretic, but it really is essentially equivalent to very hard questions in complexity theory. And so you cannot expect to do anything other than giving a conditional result. Okay, so just to conclude, you'll hear more in the next talk, but I really think this is an important aspect that we kind of didn't look at in provable security. I mean, it's not always relevant, so there are many examples of schemes that are not memory sensitive, meaning that the best attacks are memoryless, but I gave you natural examples where it's not the case. And again, so even here, right, so you see that the common thing, the double encryption doesn't help if, to get better security that you might teach in class. It's only true if you're not restricting the memory, if you're assuming that the memory is very large. As soon as you restrict memory, it actually buys you something. Okay? And that's actually where we started thinking about this question. And so there are other non-trivial things with connection to computation from complexity. For example, another thing you can look already in symmetric crypto is message authentication. You have some block cipher with n-bit output. You want to authenticate longer message and get security beyond 2 to the n queries. Then you can easily see that it already connects to building PRGs against space-bounded computation in a very strong sense. And so, which means it's not inherently impossible, but you cannot really hope to come up with anything without making a breakthrough in complexity. And there's other areas, of course, I haven't mentioned that look at questions related to memory. So Eike and Benedict were here at a paper on memory-tied reductions. They were focusing on the trivial aspect here of reducing from one assumption to the other one. Here, everything was memory-tied. But you might have, build an adversary in your reduction which has higher memory complexity, and that's high undesirable. And there are very nice lower bounds that unfortunately nobody's talking about here. And of course, there's entire memory hard function proof of space work, which can be seen as a simpler step in this direction for simpler security notion where we prove lower bounds on space-time trade-offs. And open problems here is really just finding more examples of things that are, even come up with things that are memory sensitive and cryptanalysts know about it and try to prove lower bounds. I mean, sometimes unconditional, more often maybe conditional, find the right problems in complexity you can reduce things to. It's non-obvious. And also in terms of attacks, I think it would be nice to have a common language to describe them. I mean, this is an issue that comes up a lot. I would like to have precise upper bounds on probabilities. Most attacks are formulated in a way that there are no such upper bounds. So that's lower bounds on probabilities. So it's interesting there to make the connection. All right, thank you.
So we have time for a couple of questions while
Yeah, Itai says something.
Is your proof to go to KL and come back robust to also allow some non-uniform advice?
Yeah, so right, so that's a good question. So I think the non-uniformity here, right? So in that proof, it's actually a standard model proof. So it's really hidden in the reduction between PRF security and so the encryption and you build a PRF distinguisher, right? Which has the same time space complexity. So it's not really, depending where you want the non-uniform advice. So the random function here, that you're looking at, it doesn't really make sense to think. Right, so. Right, so it's orthogonal to that, so it wouldn't be a problem because yeah, but I think you might thinking of something which doesn't really matter here. So I can talk to you offline if you want. So that's yeah. It's actually Dimas, so I stole it already. So it's a hierarchical stealing. So thanks.